Solve the following system of nonlinear equations algebraically. Here we have the system of equations 3x squared plus 2y squared equals 5, and x minus y equals negative 2. Now it's not really important, but the first equation is similar to a circle, but because of these coefficients not being equal to one another, it actually makes an ellipse. The only reason that might be important at all is simply because that could give us some intuition as to how many solutions in the end we should expect. So if I have an ellipse and a line, my expectation is at most two. There could just be one under certain conditions, or there could be no solutions, but I'm expecting two, so let's work with that. Now, to solve nonlinear systems, it's generally best to uh, use the substitution method. And to do that, what we're going to do is solve one equation for one variable. So I think I'll take the linear and solve it for x. So that would be x equals y minus 2. Then what I'm going to do is replace the x in the other equation with the y minus 2 that I just came up with. So it's going to look like this. I'm going to have 3 times the quantity y minus 2 squared plus 2y squared equals 5. So 3 times this would become y squared minus, the way I come up with the coefficient here is you square the first plus 2 times the first times the second. So this would be minus 4y. And then you square the second. It's very tempting for students just to write y squared plus 4, but you can easily show through FOIL that that doesn't work out. You always have this middle term. Anyway, then plus 2y squared equals 5. Now it looks like I'm going to have a quadratic in the end, so what I need to do is get everything to one side and combine. So let's first distribute this 3. And when I distribute the 3, of course, it's going to multiply everything inside this set of parentheses. So this would be 3y squared minus 12y plus 12 plus 2y squared. And you know what? I'll bring this 5 over. So I would just say minus 5 equals 0. Okay, so 3y squared and 2y squared, those can combine together and make 5y squared. Then negative 12y, it's the only one that I have with just a y, so minus 12y. And 12 minus 5, those will combine together to positive 7. Which leaves me with a quadratic that I might be able to factor, but if I can't factor, then I'll use the quadratic formula. Let's see what we can do here. The nice thing is the leading term coefficient and the constant are both prime numbers, which means there's not a lot of combinations to try here in the first place. So 5y and y are the only values that would multiply together to give me 5y squared. And 7, I'm going to make this 7 and 1. And the reason I'm going that direction is because when I multiply 7 times y, that gives me 7y. And 1 times 5y would give me 5y. And if these are both negative, then they will add up to negative 12y. So there's my factors. And I can set each of these factors equal to 0. So if I take 5y minus 7 equals 0, then that would give me 5y equals 7, or y equals 7/5. All right, but then I also have y minus 1 to set equal to 0, which gives me another solution of y equals 1. But these are only the y values of my solutions, so it looks like I'm going to have two different solutions here. But I need to figure out what the x value is for each of them. So you can go back to any equation, but whatever the simplest one is generally the best choice here. So I'm going to choose this one. All right, so when y is equal to 7/5, then x is that y value minus 2. So let's see here. That would be 7/5. And then I need to change 2 into a fraction with denominator 5. So I'm going to multiply it by 5/2. So 2 times 5 is 10. Then that's over 5. So 7 minus 10 is -3. So there we have -3/5 as the x location of my solution. And then when y is equal to 1, x is the y value minus 2, which is a little easier in this case. It's just -1. So then I have the x value of my other solution, and that gives me the two coordinate values where these equations intersect one another.